So you've clicked on this video. There's a couple reasons why I'm guessing. You're either a grader from the Berkeley Math Tournament, one of my truly obnoxious 8 subscribers, or because you're trying to learn this for a class or competition. Hello there if you're the grader. Well, where to begin? For those of you who are new to learning about mass points, I'm definitely going to teach you about it starting from the very basics. But I hope that you get to learn a little more beyond the problem on the paper and observe how beautiful geometry can be. Now, I'm going to start from the very beginning as to what mass points are. A funny name, isn't it? Maybe it's these fireworks starting at a point and then breaking up into masses. Or these large round points of masses. Or maybe these numerous small points of masses. Or maybe even these millions and billions points of masses. Perhaps I'll add a black hole as a massive point, and that'll be a group of mass points. Though, if it's a black hole, it'll probably be pointless, dare I say. Maybe it's this group of interconnected points. But enough of that, as what's the point? Let's take a trip back into history to figure out the background of mass points. Mass point geometry was invented by Franz Mobius in 1827. However, it didn't actually become popular until the 1960s when New York high school students made it popular, which is why we decided to teach this topic as we are also high schoolers. Mass points is a technique in geometry that can greatly simplify the proofs of many theorems concerning polygons and is helpful in solving complex geometry problems involving lengths. In essence, it involves using a local coordinate system to identify points by the ratios into which they divide the line segments. Don't worry if this sounds confusing. We'll explain it with an example. Now, back to our regular program. No, not this one. Not this one either. There we go. So let's start learning through observing a problem. The problem is in triangle ABC, D is on AB such that AD equals 4 and BD equals 3. E is on BC such that BE equals 5 and CE equals 4. If point F is on AC such that BF, AE, and CD intersect at the same point, what is the ratio of AF to CF? We can solve this problem with a strategy called mass point geometry. This strategy utilizes the concept of mechanical advantage. So, what is mechanical advantage? Consider this simple experiment of opening a door. Open it once by applying a force where the doorknob is, and open it a second time by applying a force near the hinge. You'll find that it was much harder to open the door near the hinge. This is because forces further away from the pivot have more impact, which is why it was easier to open it farther away from the hinge. This is also why doorknobs are attached at the end of the door, a location farthest away from the pivot. The mechanical advantage formula states that if you have two objects on a balance, and if one point of mass m1 is placed a distance x1 away from the pivot, the other mass must satisfy the equation m2 times x2 equals m1 times x1, where m2 is the mass of the second object and x2 is the distance away from the pivot for the second. And so mass point geometry involves systematically assigning these weights to points using ratios of lengths relating vertices, which can then be used to deduce other lengths. We can apply the same concept to this problem. The way to systematically assign weights to the points involves first choosing a point for the entire figure to balance around. From there, a first weight can be assigned. From this first weight, others can be derived using a few simple rules. Number 1, any line passing through the central point will balance the figure. If 2 points balance, the product of the mass and the distance from a line of balance of one point will equal the product of the mass and distance from the same line of balance of the other point. And if 2 points are balanced, the point on the balancing line used to balance them has a mass of the sum of the masses of the 2 points. Though we won't really be applying this principle for now in this specific problem, but you'll see in other different problems. So now let's return back to the problem we talked about previously. So first, let's attach 3 masses such that the point where the lines intersect is the balancing point. Let's assign a value of 4 to the point mass on B. By the mechanical advantage formula, the mass at A must be 3, as 4 times 3 equals 3 times 4. The mass at C must be 5, following this exact same principle. Now we can apply the mechanical advantage formula to side AC. The masses A and C are in a 3 to 5 ratio, which by mechanical advantage means that AF and CF need to be in a 5 to 3 ratio. So congratulations, now we've solved the problem. Now let's think back to the very beginning of this video where I showed you a lot of confusing points. Are you seeing how math points can be applied now in these cases given the correct information? And in this simulation here too. It's everywhere around you if you just look for them, and there's so much more you can explore. We hope you've learned something and have a greater appreciation now of the beauty of mathematics. Thank you for watching.